Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, class. Welcome to your first SIC2003 virtual physical chemistry lab. Now, obviously, this is a new experience for all of us, but let's hope that everything will go on well and we're going to learn as much as we can. Okay? So let's get to the core business for today, which is experiment 1. Today we're going to talk about thermodynamical properties of liquid vapor phase equilibrium. Now, in case you don't have the physical lab manual, you can always get that from the chemistry website. And the current student, you can actually get it from the lab manual there. Alright, so today the objective of this experiment is actually to find the value of the delta S vaporization for third butyl alcohol. Okay, and so in order to do that, you're not going to get this value directly by doing the experiment. So after the experiment, if you're in the lab, okay, you'll be plotting, and then from the plot you will then need to do some calculation, and then you will get this the entropy of vaporization for third butyl alcohol. Now, to lead to that value, to this entropy, so the relationship of this, the entropy of vaporization at the boiling temperature of a liquid, is related to its enthalpy of vaporization. So as you have learned in physical chemistry 1, the relationship between delta S is that it is equals to the enthalpy of vaporization over the boiling point. Okay, so this is what you are going to get in your plot, and from this you can actually use this expression to get delta S. So it's very straightforward. Alright, on top of that, there is this rule called Trouton's rule, which states that most liquids have similar entropy of vaporization, which is about 85 joules per Kelvin per mole. Now, with exception, like for example hydrogen bond and metallic bond, so else most of them actually have similar delta S. So this is something I want you to do a little research on to understand why is that so, because that's very important when you want to discuss in your lab report as when you start doing it. So do find out why do they actually share this common delta S vaporization. Alright, so if you go through the lab manual, okay, there are a series of equations which actually intend to derive the Clausius-Clapeyron equation. So the derivation isn't complicated, so just go through those equations and it will lead you to this equation. Alright, so in order to plot this, it's easier to actually integrate this, and if you actually integrate this, it will give you a natural log of minus delta H over RT plus C. C is the intercept. So it's minus, so the integration of, for example, 1 over x squared will give you minus 1 over x. So the integration of 1 over t squared will give you minus 1 over t, as you can see here. But there is this 2.303 as a divisor. As I said, this integration gives you the natural log, but your lab report shows this integrated in the form of log. So the conversion, so this is just the divisor 2.303 is just the conversion of ln p to log p. Okay, so you see this value as a divisor or multiplier a lot in physical equation. So it's because of that, the conversion of log p ln P to log P or log P to ln P. Okay, so there you go. So this is the equation that you get. Obviously this looks like a linear equation, all right, and so this is going to be your y. Your y is going to be log P. M, the slope, is going to be minus delta H over 2.303 over R, and C is going to be your intercept. So hence from this plot you can actually get the value of delta S, right? As you plot log P versus 1 over T. Okay, so now don't we just miss our department? Okay, so this is our lab. Oh my god, I'm really missing this place and I'm sure you do. I hope you do. So this is the setup. Okay, the setup for experiment 1. So, well, we can't do this, so I'm just going to explain to you what's going on here. So this is where the third butyl alcohol is going to be. So there are boiling chips in here so that it will boil evenly. Okay, so it's wrapped with aluminum oil so that it's the vaporization process is contained in there. So now this thing is so you have the Liebig condenser here. So now this is what we call the vacuum line, right? And this is the manometer where you actually the highlight of your getting the data, all right? And this is just a so this is just a protection so that to avoid the third butyl alcohol from going to the vacuum pump. So this is it's actually much longer. We should see the vacuum pump somewhere in here. All right, so in essence, before you actually do the experiment, so if you can actually see it very close here, so inside the manometer is your mercury, liquid mercury. So and here, which you can see, so this is where one part of the manometer is open to the atmosphere. So this is what PATM is going to be, and one part of it is actually connected to the system. So this part is actually closed. But before anything is done, the level of the mercury for the ATM and the system is the same. That means the pressure of the atmosphere is the same as that of the system. Okay, so before you actually start the experiment, so the experiment involves changing the values of this the system. All right, so remember that PV is equals to nRT. All right, so if you increase the pressure, you're also increasing the boiling point. So it's not wise to start the experiment by having a high pressure of the system, because that involves a high boiling point. And when you have a high boiling point, it's not easy to actually cool down because it takes time. So it's better to start at a low pressure of the system and then slowly increasing. As you actually increase the pressure, then this system is going to stop boiling. So before you actually do that, how do you actually lower the pressure? Now the easiest concept to remember this: the more air space in here, that means the higher the pressure. So same pressure here. So in order for you to lower the pressure of the system, you need to raise this up, raise this mercury level up, so that you only have a short distance of air in here. So that means you have low pressure in the system. In order to do that, you have to what you call close the air, close the tap for the air and then connect it directly to the pump so that it will actually suck up, and so that will actually increase that. Then you close the pump and you can start the experiment by actually start boiling. So at the start of the temperature, okay, at the start of the pressure, it will start boiling, and then you'll record what is, and you will see vapor coming out, and then when it's stable, you will actually measure the difference. We'll talk about the levels later, but in essence, that's how you do the experiment. Okay, and what else? Okay, all right, now that you have gotten one value, so now you need to actually get a second set of value. In order to do that, you need to increase the pressure. So you start increasing by introducing some air into the system. So this is air, right? So this step is connected air, so open it a little bit, and so this will start actually increasing. So the first it starts at here and then it starts increasing, so you have increased the pressure of the system. When the pressure of the system increases, this third butyl alcohol will stop boiling, because remember, now it has a new pressure. New pressure means new boiling point. So then you wait until it boils, get the value of the boiling point, and then get the final value of the difference between the two levels of mercury, and which is the pressure of the manometer, and so and then you start increasing again. So it's a subsequent it's a continuous experiment of increasing the pressure of the system, and then get the value of the new boiling point. So if you get up to at least, up to 8 to 10 points, that's good enough for you to start plotting. Alright, so there you go, our physical chemistry lab 2. Right, so this is just looking, you will need this because it's quite difficult to actually look at the little numbers and the lines. So this actually helps. This magnifying glass actually helps. Okay, so in essence, in the manometer, if you have the two levels of mercury being equal, so you're saying that P1 is equals to P2. Now I'm sorry that my drawing is a little bit, so this is really hand drawn. Okay, and so it's supposed to be equal, but you get a picture. So if P1 is greater than P2, so you see that there's more space here, more airspace here. So it's just a simple way to remember. If there's more air, more pressure. Alright, that's an easier way to remember. So this is less air here, so less pressure. So P1 is less than that, so less air here, so this one is more. Right, so in terms of the if you have, for example, okay, P1 and P2 again, so this is the level for P1. So if you actually go across here, so P1 is this whole thing, right? So it's equivalent to the pressure of the manometer. In this case, manometer, the mercury inside, which is related to the height of the mercury in mmHg, and also plus that of the pressure of P2. So P1 is actually equals to Pm plus P2. Now in our experiment, P2 is connected to the system, P1 is the atmosphere. So if you actually plug that into this equation, so P2 is equals to P1 minus Pm, and the P system in which we are interested in is actually equals to the P atmosphere minus that of the P manometer. And the P manometer that you measure, the difference between the energy levels sorry, the difference between the mercury level is the P, is what you measure. Okay, so if you start at a low pressure of the system, okay, then the third butyl start boiling, and then when you actually introduce this air, this will be, so this level will be lower, okay, and this one will increase, so then you have, you know, a much lower H there. So and then you have a new boiling point, because now the pressure is a new pressure. So as I said, PV is equals to nRT. New pressure means new boiling point. So that's how you actually do the experiment. Okay, so here is a data that that is given. Okay, so let's take the atmospheric pressure to be 750.49 plus minus 0.05 mmHg. So these are the obtained values of the boiling point, and this is the H that one measures for each subsequent boiling point. Okay, so there are 9 points here. All you have to do is actually get the value of the system, which is simply PA minus PM. Okay, that is very easy. Just translate this, transfer this into Excel. Okay, and then get the values for the log of the system. Log P here is log of the system. So, and then get the value for 1 over T. So what you're going to plot is actually log P over 1 over T. So what I want you to do is calculate the enthalpy and entropy of vaporization of third butyl alcohol. Determine from your graph the boiling point of third butyl alcohol, and via calculation, that is, and comment with respect to Triton's rule. Okay, so the contents of your report is you have a cover with title, name, new matrix number, objective, what's the objective, okay, completed data and calculations, then your plot, a brief discussion, and references. That's it. So this is due by 20th May, and I forgot to mention that this needs to be this is sent via email, and I will give you the email address in the WhatsApp group. Alright, so that's all for today's lab. So if you have any questions on the report contents and so on, you can always WhatsApp me. Alright, so Carpe Diem. So I'll see you in the next lab next week then. Alright, good luck and see you. Bye. Assalamualaikum warahmatullahi wabarakatuh. Thank you.